Hello everyone, my name is Zhen Li. I'm a research scientist in the PyTorch team. Today I will talk about PyTorch distributed package and will focus on RPC, which is a new feature that we introduced this year. I will first briefly explain what is PyTorch RPC, and then go through some basic RPC APIs. After that, I will present high-level ideas of how to implement different training applications using RPC. Alright, so what is PyTorch RPC? PyTorch RPC is a low-level framework for general distributed training. Before RPC, distributed data parallel, or DDP, has been the main feature that PyTorch offered for distributed training. However, DDP is one specific training paradigm, where every process has a full replica of the model, and you split the input across multiple processes. It works for many applications, but there are also many other applications that do not fit into DDP. For example, if your model is too large for one machine, you will need multi-machine model parallelism, which does not work with DDP. You will have to manually send intermediate outputs and gradients across processes and also resume autograd in application code, which can become very complicated. Another example is that sometimes we need to mix parameter server with DDP, using parameter servers for sparse tensors and DDP for dense tensors. This cannot be easily done with just DDP. One option to solve this problem is by adding a different feature to support each of these use cases. Nevertheless, if we did that, it will create a large API surface, which can become a hurdle for users to pick up. And it will also create a high engineering overhead to write and maintain. Moreover, we cannot fully anticipate what new training paradigms might emerge in the future. Another option is that we can provide a set of flexible low-level tools which would allow users to improvise. So here comes PyTorch RPC. We hope it can fill the gaps for the distributed training applications that cannot use our DDP. And if some new distributed training paradigm becomes widely adopted, we always have the option to introduce a dedicated high-level API for it. So now we know why we introduced RPC. Then, what features do RPC offer? As of 1.7, there's already a long list of features in RPC package, but I will only focus on the most basic parts in today's talk. The first one is remote execution. This allows you to run a user function on a specific remote process, which is what you would expect from any RPC system. The second one is remote reference, which allows you to reference a remote object and pass it around using remote execution without transmitting the real data. It serves as a distributed share pointer. The third one is a distributed autograd. It will stitch together local autograd graphs of remote executions into one distributed autograd graph, so that when you call backward on a loss tensor in one process, it will reach out to all participating processes and machines and compute gradients accordingly. That's a very high-level explanation. Let's now dive into more details. Remote execution. It allows running a callable remotely. In PyTorch RPC, all processes are peers. Any process can be both caller and callee. After initialization by calling init RPC, any process will have a message listener running in the background and use a thread pool to process requests and responses. After that, there are three ways to run a callable remotely: RPC sync, RPC async, and a remote. RPC sync runs RPC synchronously. It will block until the return value is available on the caller. RPC async, on the other hand, immediately returns a future object of the result. The third API is remote, which also returns right away, but instead of returning a future object, it returns a remote reference, which can be treated as a distributed share pointer of the result. The difference between RPC async and a remote is that the former will always fetch the result back to the caller, but the remote API does not do that. The remote reference will keep the result alive on the callee. The code in this slide shows how to pass different types of callables to RPC APIs. It can be PyTorch built-in operators. It can be user Python functions. It can also be script functions. If performance is a concern, please use stripped functions, as there won't be a contentions on the global interpreter lock, meaning that different RPCs can run concurrently on the callee. Remote reference. A remote reference is like a distributed share pointer. It points to an object on the local or remote processes and will manage the lifetime of the data object using the reference counting. This is useful when a caller would like to directly forward the output from the callee to another process and avoid fetching the real data back to the caller. In the example, worker 0 is acting as a coordinator process. It sets up data dependencies across 4 other processes, and none of the real data object goes through W0. The white dashed arrows are lightweight RPC remote calls, and the bold red arrows are heavyweight data paths. Let's look at one of the remote calls, the one from W0 to W3. The arguments RA and RB are remote references of outputs from W1 and W2. When using RA and RB as arguments in the RPC API, the RPC system will automatically fork RA and RB on W3 and increment the reference count accordingly. Then, on W3, it calls to here to fetch the real data from W1 and W2, which will block until the data is received in W3. In this way, the remote reference allows W0 to asynchronously and efficiently set up function executions and data dependencies in a distributed environment. Remote execution and remote reference help applications to piece together forward paths across processes and machines. Another important component in PyTorch is the autograd system, which powers the backward pass. The RPC framework extends local autograd engine to work in a distributed environment, and it also provides distributed optimizer to update all parameters involved in the application. One difference between local autograd and distributed autograd is that instead of storing the gradient in the parameter.grad field, the distributed autograd engine stores the gradients in a dedicated context, and there can be multiple autograd contexts coexist for the same set of parameters. The reason for this design is because there can be multiple concurrent backward passes sharing the same parameters, and when this happens, we'll need to make sure that these backward passes do not step into each other's toes. Hence, in order to use distributed autograd, you need to first create a context. All RPCs made within that context will carry the context ID information, which will help callers and callees to find each other in the backward pass. In this toy example on the right, it first uses 2 remote calls to create 2 parameters and initializes the distributed optimizer using the list of parameter remote references. After that, it runs the forward pass by simply fetch the parameter from the owners and then sum them together. Then it feeds the loss tensor to the distributed autograd backward function, which will compute gradients for all parameters in the distributed autograd graph and store the gradients in the context. Finally, we can pass the context ID to the distributed optimizer step function, which will reach out to owners of all parameters, retrieve corresponding gradients from context, and update parameters using the provided local optimizer. In this case, it's SGD. As you can see, the APIs for distributed training is very similar to local training, except that you will need to create a context for it. Given all these new tools, what can you do with them? It unlocks many distributed training scenarios on PyTorch, and I will briefly describe 3 of them. The first one is a parameter server, where you can have one parameter server or several sharded parameter servers holding the parameters, and then there can be multiple trainers running training iterations. The RPC framework can help link them together. Another example is a distributed model parallel, where the model might not fit in one machine. In this case, you can divide the model into multiple submodules and use RPC and RF to piece them together. The third example is pipeline parallelism. You can use the asynchronous APIs in RPC to process one batch and then run iterations on multiple batches concurrently. Tutorials are available for all these use cases. All right, that's a very short introduction of PyTorch RPC. With this talk, I want to make sure that at least I deliver one message to you, which is, if DDP does not sufficient for your use case, please try PyTorch Rpc. We have quite a few tutorials, and we also have an extensive API page. We are actively monitoring GitHub issues and forum questions for RPC on a daily basis. So let us know if you encounter any problem, and also let us know if there's any way that PyTorch RPC can be improved.